Okay, so let me welcome everybody. Welcome and thank you for joining us today for the weekly Institute of Astrophysics Astrophysics seminar. Today I am in the particularly wonderful position to be introducing one of our very own here, Dr. Vincent Pelgrims, who obtained his undergraduate degree at the University of Mons in Belgium, and then moved to the University of Liège for his master's and PhD work. His first postdoctoral appointment was in Grenoble, after which he made the excellent choice to join us here in Crete. And so today he will be talking to us about some new and exciting results regarding galactic foregrounds to the polarization of the cosmic microwave background, which is clearly a topic for which here in Crete we care dearly about. So without any further ado, Vincent, the floor is yours.
Hi, thank you. Thank you, Vesa, for the very nice introduction. So indeed, I will speak to you about galactic foregrounds to the CMB polarization and give a general introduction to this topic. And so work that I've been doing for the last 4 years now. So including all those collaborators that you can see here. And then I will move to speak specifically about frequency decorrelation and how we burn a full haystack of data to get a needle. And that work has been doing in collaboration with people in light blue that you can see here. So yes, I will start with an introduction about cosmology and then move forwards. So what about cosmic microwave background cosmology? And what about cosmology in general? Well, we all have in mind that, the Big Bang scenario in which the universe, time and space originate from a Big Bang, a singularity, and then the space expanded very rapidly with an inflation phase, and then everything grew with time. So this very nice picture where we have galaxies and going back in time, where we have nothing in the dark age, and then we have this bright surface called last scattering surface or cosmic microwave background, because we can see it today at the microwave wavelength, which is the first light that we can observe from the universe. And the cosmic microwave background is a unique probe of the early phase of the universe, so everything that happened before this first release of photons. But also it is a very good tracer of the history, the full evolution of the universe, because the photons that were emitted at the last scattering surface, they do had to travel through the whole universe. And so they carry all the information of the history of the universe. And this is a map, a full sky map in galactic coordinates of the CMB in intensity and here in polarization, because yeah, and the CMB has been a very strong probe and a strong success for cosmology, because it showed that the Lambda CDM, so the current best model of the evolution of the universe, works very well at explaining the data. And this can be shown in these power spectra here, which are basically only a very simple, not simple, but a way at looking at this map here. So it is this curve here in blue are from a 6 free parameter model called Lambda CDM. And as we can see, it explains well the data that is observed in the full sky map. Okay, and this is true in intensity, and it was already true back to the previous CMB experiments. And it's even more correct for with Planck, for instance. Planck has characterized this power spectrum, and so the full history of the universe with a very high accuracy. The story is slightly different in polarization, and I will quickly show you why. But here, yes, so the CMB is polarized because of all the inhomogeneities and anisotropies at the last scattering surface. But this polarization is very weak and so difficult to measure. Nevertheless, there is a huge interest for CMB polarization because it is the unique probe of the primordial inflation phase that happens so before the last scattering surface and well in the very early phase of the universe. And the reason is that an inflation produced gravitational waves that that left their imprint on the polarization pattern that can be observed on the CMB. And gravitational waves are the only the only sources of what is called the B modes in the polarization. So here in this map where we see the CMB polarization, you can see ripples and wiggles perhaps, and this can be decomposed in two different modes, the E mode and the B mode, which have a different parity, well, which have a, how to say, so the B mode get a minus sign under a parity transformation, and they correspond to such pattern in the polarization. And only tensor modes of, so tensor perturbation of the space-time can lead to B mode, while an inhomogeneity in the space-time, so the presence of a black hole, for example, will produce only E modes. But the B modes by nature are expected to be very, very small. And so, but yeah, sorry for the confusion. So there is a huge interest at searching for B modes because the detection of primordial B mode would be a direct proof for the inflation phase. So at the very beginning of the history of the universe. And this is the last confirmation that we are waiting for to prove somehow that the Big Bang scenario is a viable scenario. Inflation models predict a non-zero tensor to scalar ratio, which is a perturbation of gravitational waves to other scalar perturbation. And this is directly related to the ratio of power spectrum in the polarization. So the ratio between B modes and E modes. And the recent status on the search for those B modes is presented here in this graph, which is already a little bit old, but still, where we see that there is no detection of the B modes. All those triangles here present upper limits of a measurement at a given multiple, so a given separation in angular separation in the power spectrum. And the only the thing that we have to note here, sorry, so is what we expect for an inflation, a simple inflation model with a tensor to scalar ratio R of 0.01% is the dashed line here. And what we see is that we have detection in this corner here. And this detection here are actually the signal that is due to gravitational lensing. So the photons are emitted at the last scattering surface, and then they cross the universe. And so they are perturbed by the gravitational well of large-scale structures. And this gravitational lensing produce a leakage from the E modes of the polarization to the B modes of the polarization. And that is well known and well predicted by this ascending curve here, okay? So this is known. And there is also other point here, the green point from the Bicep and Keck observation in 2014, which first claimed for a detection of something that looked like the detection of primordial B mode. But soon after that, people realized that this was only the signature of galactic foreground from the magnetized ISM, because indeed, photons that are emitted here and so that carry information from the inflation, they are then perturbed by the full matter content in the universe. And then they had to cross the galaxy, because we are living in a galaxy, and the galaxy is made of matter and magnetic fields. So there is, in our own galaxy, emissions that are polarized and that add up to the cosmological signal. And these emissions are known to be galactic foregrounds from magnetized ISM. And which means that instead of looking at the CMB like this, as cosmologists would dream of, we see such a sky here, for example, here at 353 gigahertz, where the only thing that we see is the dust polarized emission from our own galaxy. So it is clear that dealing with galactic foregrounds in polarization is a challenge. And through frequencies, there is known at which the CMB is more bright than the foreground from the galaxy, either the thermal dust at high frequencies or the synchrotron polarization emission at lower frequency. So the CMB polarization is always subdominant at all frequencies and at all scales, which is important for cosmology because all the cosmological model is characterized by a power spectrum, which means the power, depending on the angular scale at which we compare the pixels, say. And what we see from this Planck result here is that at any value of the multiple, the E mode and the B mode in the polarization of the CMB are always below what is below the contribution from the foregrounds. Here, the dust at different frequencies, different frequency, or the synchrotron. And the situation is even more dramatic when we speak about the B modes, as we can see here. For example, a model, inflation model with a R value of 1% is way below the signal from the dust, like 2 orders of magnitude below. So it is clear that one has to deal with galactic foreground, and one has to remove the foregrounds in a way to get to get the information from the CMB, the cosmological information. And this is known for some time, and so people have developed what is called component separation algorithm that take observation of the full sky at different frequencies, and then that characterize the spectral, the SED of the emissions, and that rely on some hypothesis and assumption, and then that allow to really remove this veil of galactic emissions to access the CMB observation. But those algorithms, those methods, it is clear that they have to, the accuracy of those methods needs to be tested against all the hypotheses and assumptions that on which they are built. Okay, and the only way for me to test the accuracy of such a method is to call for modeling of the foregrounds. If we have a good modeling of the foregrounds, and in what concerns me, good modeling of this sky, the polarized galactic foregrounds, then we can put them, we can ask the component separation method to prove that they work even in realistic case, and that they can accurately give us back the CMB. So for the last few years, I have worked on the modeling the galactic magnetic field and the matter density distribution from such data sets. So because these data sets were taken for CMB cosmology, we have those data sets, and those data sets contains information from the magnetized ISM. So let's use those data sets to constrain model of the galactic magnetic field and the dust density, for example. So I say the word galactic magnetic fields. The galactic magnetic field is the magnetic field in our galaxy, and we know it has an important role in different places, physical processes in astrophysics, like cosmic repropagation in the galaxy, but it has also an important role in the formation of stars and the stellar system. It may have a role in the structure and evolution of the galaxy. And as I just discussed, it is important for extragalactic, for the analysis of extragalactic signal as well. But unless it's important role in many physical processes, only little is still known about the origin of the galactic magnetic field, the structures, and its strength. So with my first postdoc, I started using those galactic emission to constrain the galactic magnetic field. So the goal is and was to take those data sets and to constrain three-dimensional model, parametric model from those data sets. So producing three-dimensional galaxies, integrating them along the line of sight to produce two-dimensional observation like this, and compare with the data. And I did that in those paper, and we kind of quickly realized that we are limited by the parametric models that we can use. Here are the best fit, the obtained best fit of 4 different galactic magnetic field model. We can see that they share similarities, which is good, but they are a bit different. And the methodology cannot tell apart which is the best. But it is clear that those models here would be very far from being realistic. Then, after I realized with Rafael Skalidis at the University of Crete that the high galactic latitude of the dust sky was dominated by a dusty and magnetized structures close to the solar to the sun, called the local bubble, I start playing with a different kind of approach to model the magnetic fields. And I use three-dimensional data set from extension data to constrain the geometry of the local bubble shell, as it can be shown in this video here. And then I use that shape to constrain the magnetic field in the shape of the local bubble. And as you can see on those maps here, where we have the data and the best fit, we kind of obtain a good model of the dust polarization sky at high galactic latitude according to this approach. However, and as I already said, in this business, we encounter strong limitation. The thing is that we want to do three-dimensional reconstruction of the galaxy from two-dimensional data sets. The diffuse emission result from this line of sight integration, and the parametric models are way too simplistic. In a way, we need to break the line of sight degeneracy and to move to actual three-dimensional inversion. And in this business, we can use stars as a distance candle through the ISM, because polarized dust emission and starlight polarization, they are due to the same dust in the galaxy. And this is sketched in this panel at the middle here, where we have a cloud of dust. The dust grains are those small ellipses here, and the cloud of dust is permeated by a magnetic field that is horizontal here. The dust grains in the ISM have a tendency to align the shorter axis with the magnetic field. Okay, and it is because of that alignment, so preferred direction, that the emission from the dust will be will be polarized, and that the polarization of the dust will be preferentially perpendicular to the magnetic field projected on the sky. So at radio wavelength, the microwave wavelength, the dust will emit here in this sketch vertically. While if we have a star in the background, a star that emits light that is unpolarized, that light will be diffused, scattered in an anisotropic way, and this direction of the electric field will be more absorbed than the other one. So the light will get an effective polarization that is here horizontal, so parallel to the magnetic field. That is to say that the polarized dust emission and the polarization of stars, they are correlated. And so they can be used together to constrain what is going on in the magnetized ISM. And ideally, if we have many stars along the line of sight, well, in a beam of observation, and if we have different clouds here, we could, in principle, be able to decompose the ISM in slices and infer what is the properties in terms of magnetic field and column density of a first cloud and our second cloud. And ideally, if we have enough stars, do such a kind of deep projection in distance, where here we have the polarized dust emission the polarized dust emission in the submillimeter. And here it would be the deep projection in three dimension that could be obtained from the stars. This is an idealized picture, of course. But perhaps soon we will be able to do such kind of things thanks to the PACIFY survey, which is an international collaboration that we know well here at the Institute of Astrophysics, because it is an international collaboration with ED at the EF4 by Costa Tassis, and then that involves people in India, in South Africa, and in the US, and also a team in Norway. And PACIFY is a survey that is planning to observe the sky, the star polarization, with two instruments, one at Skinnacas Observatory in Crete and the other one in Sutherland in South Africa. What is good with PACIFY is that it is coming on soon. The commissioning is planned for in a few months. And PACIFY will ideally measure the polarization of more than 1 million stars at the high galactic latitudes, so the regions that are important for galactic foreground science. And it would, in principle, allow for a 3D inversion of the galactic magnetic field and of the dust by combining this polarization measurement with the distance of Gaia. And the ultimate goal of the PACIFY survey is to use starlight polarization to clear the path toward the detection of CMB modes that are so important in cosmology. To show that an inversion of the dust sky is feasible using starlight polarization, Panopoulou and collaborators demonstrate. So 2 years ago, that the starlight polarization can indeed be used to have the projection of the dust magnetized ISM. And to do that, they point the Robopol telescope, the Robopol instrument at Skinnacas telescope, to measure hundreds of starlight and the polarization of hundreds of stars in two lines of sight that were pre-selected based on H1 data, so that one of those sight lines had to cross two different clouds, while the nearby one had to cross only one cloud. And what they did is to show that combining those measurements, those measurements of starlight polarization, they were able to reconstruct the plane of sky orientation of the magnetic field in each cloud happening in the two cloud line of sight, and to constrain the column density and the distance of each cloud. So of each cloud, yeah. So this demonstration was a very good news for PASTIFY survey, because it tells indeed that a three-dimensional inversion is visible using starlight polarization. But this observation might also be a good study case for a different kind of businesses, which is related, and which called for the line of sight frequency decorrelation of dust emission. So what is this? Back to 2015, Tassis and Pavlidou remind the CMB community that since dust emission is a modified blackbody, and that the polarization of dust is linked to the magnetic field that permeates the dust clouds, then if we have multiple clouds along the line of sight, and that those clouds have different SEDs, that means different temperature or dust emissivity, and if the magnetic field permeating those clouds are misaligned, then we expect to see a frequency dependence on the polarization angle of the dust emission. And the reason they do it is to remind the community that there might be a danger in extrapolating polarization pattern from one frequency to another, which is something that is been routinely done in the CMB in the CMB community when one has to deal with foregrounds and or characterizing the observation. What Tassis and Pavlidou further did is they studied that effect and demonstrate the principle of the line of sight frequency decorrelation as due to multiple dust cloud. And they show that the effect might be more severe if the magnetic field is misaligned by an angle that is more than 60 degrees, as it can be shown here, where we have a different misalignment of the magnetic field in the plane of the sky, and for a ratio of polarized polarized intensities of the two different clouds here. So that effect might be important for CMB polarization studies, but so far had never been studied. In this study, they show that we have two clouds that are superposed along the line of sight, and that the magnetic field is away by something like 60 degrees. So it might be a good candidate to search for the effect that was predicted 5 years ago. So what we did in this paper that will be submitted soon is to look for EVPA differences for the two cloud line of sight here, and in the Planck in the polarization data from Planck. So here the color show the difference in EVPA between the 353 GHz polarization map and the 217 GHz polarization map. And the mean value of EVPA difference, when we account for the noise, is here at about 8 degrees for the two cloud line of sight, while it is compatible with 0 for the case of the one cloud line of sight. So we can see, or we can claim here for a hint of EVPA difference between the two frequencies at more than 2 sigma, accounting for the noise in the detector. And we repeat the analysis with different estimate of the CMB, which start to be important at 217 gigahertz. Okay, but is this sufficient for the community to start wondering about this effect in foreground modeling and or in CMB business? Well, maybe not, because it is a single line of sight result. So it might be a statistical fluctuation, and Planck systematic, for example, can eventually could explain this this difference. So there is a lot of work to be done yet before one can claim that this this is actually line of sight frequency the decorrelation. So an idea is to wait for the pacified dataset to be available, so that we can have a large amount of lines of sight where we know that there are two clouds of dust that with a magnetic field that is strongly misaligned, or we can move forward now using H1 data. What are H1 data? Well, H1 are H1 data are data from the gas that is in the galaxy. So we know that the galaxy is filled of neutral gas, hydrogen, and there have been observational evidence showing that the dust and that gas, they are strongly correlated in the diffuse ISM, as it can be shown here, where we have the extension by the dust as a function of the column density of H1 emission, and we see that they are very correlated, which means that where you find gas, you will find dust. The good point with H1 data is that there are existing large surveys, so there are a lot of data out there, and that can be studied. And H1, I'm sorry, H1 allow one to have access to the velocity of the gas from the Doppler the Doppler shift. So we have, for each sightline, we have a spectrum in velocity and if one assume that velocity a given cloud has a given velocity, one can proceed to a decomposition of the data in terms of clouds along the line of sight. Another interesting point for us about H1 data is that it has been shown observationally that the H1 gas form some some filamentary structures, fibers, and that those fibers have a tendency to be aligned with the plane of sky magnetic field. That means that combining data set, so decomposition of clouds along the line of sight and inferring the magnetic field orientation, one could eventually proceed to 3D inversion of the magnetic field in the galaxy. And there have been pioneering work in this direction in the last 2 years. One is from Panopoulou and Lens, who proceed to the decomposition of H1 velocity spectrums along the line of sight, and so derived the number of clouds in each toward each lines of sight that are represented on this map here, where we have the north hemisphere in the left and the right, and the south hemisphere in the right, and where yellow means that we have 7 clouds along line of sight here, and the dark blue is one cloud. Oops, sorry, sorry. And beside or in parallel, Susan Clark and Brandon Hensley used the H1 fibers, the fact that the fibers align with the magnetic field, to try to decompose the magnetic field in three dimensions. Yeah. So here what we are showing is the H1 based Stokes parameters so from H1 data, what would correspond to intensity Q and U in dust if we integrate the full velocity range, and so they produce such a map in each velocity beam, yeah. And they show, what they show, they further show that if we integrate everything through velocity, we got maps, IQ and U maps that really look like polarization maps from the dust. So they confirm the correlation of H1 data with the dust data. And this is not only a matter of intensity, this is also a matter of intensity, so of density of dust and cloud, but this is also a matter of orientation of the magnetic fields, because the polarization are correlated one another. Okay, but in our concern, to what concern the search for line of sight frequency decorrelation, one can think about using those data sets to build, well, to point out line of sight where we might see the effect of line of sight frequency decorrelation. And this is what we did in the paper here, where we use, so the data set that I just mentioned, to build sample of pixels. One sample called control sample, where no line of sight frequency decorrelation is expected, because we built it as being lines of sight where only one cloud dominates the signal in intensity. And this is sketched here. We have one peak in velocity, so maybe one cloud, and the H1 orientation data can give us the orientation of the magnetic field. And the second sample of line of sight is the sample called the target sample, which are pixels where the likelihood of seeing line of sight frequency decorrelation is maximized, because we asked for pixels where there is at least two dominant clouds with a magnetic field that is misaligned, but by at least 60 degrees. This is sketch here. And we proceed to two different implementation of the building of this target sample. One relies on these complexity parameters defined by Panopoulou et al. And where we integrate the orientation data in the low velocity cloud and intermediate velocity cloud ranges are also defined in that paper. And the other is corresponds more to this picture, where we define a cloud column density and orientation by integrating the data about the centroid of the velocity peak. Okay, so we have two definition of target samples. So on the sky, this is a visualization of the sample on the sky, where here we have the white pixels are those in the target sample, and we see that they are scattered unevenly through the sky. There are lots of pixels in the north, which is well understood, and the control sample are in red, and what is in black is all pixels that are that have more than one cloud, but where the magnetic field is in the different clouds is not making an angle more than 60 degrees. Okay. So what we did then is to take this sample of pixels. Yeah, one thing to be noticed is that this selection of pixel is fully agnostic to polarization data. But now that we have a definition of lines of sight where to look for, we move to polarization maps at 353 and 217 gigahertz from Planck. And we want to ask the question whether or not we can see a line of sight frequency decorrelation by looking in those sky region. What is to be expected? First, we expect a depolarization, because if we have two clouds that are superposed along the line of sight, and that these clouds from an angle of, so that the magnetic field in those clouds is at an angle of 90 degrees from one another, the polarization will be 0, right? If the angle is smaller than 90 degrees, then we start seeing some polarization that will be a mixture between the two clouds. So if we take a sample of pixels, we expect to see a decrease of the degree of polarization in the sample where we have more than one cloud, as compared to the sample where we know we have only one cloud. And then if there is SED variation, that means if there is if the clouds along the line of sight have different temperature or different emissivity, then we expect to see an EVPA rotation across frequencies, as I showed you for the case of the two line of sight cloud. The two cloud line of sight in the previous case. But now, if we have an ensemble of line of sight, then then all configuration are possible. And what we expect is an increase of the dispersion of EVPA difference as compared to when there is no when there is only one cloud. And this is everything is actually observed when we move to the polarization map. Here we show in the orange histogram is the degree of polarization in the target sample to be compared with the degree of polarization of the control sample. And we see that indeed we have a smaller degree of polarization, statistically a smaller degree of polarization in the target. And this is also observed in polarized intensity at the two frequencies. And here we show the distribution of EVPA differences as measured between the two frequencies. In orange for the target sample and in blue for the control sample. And what you can see by eye is that the spread, the dispersion of EVPA differences in the case of target, it's much larger than in case of control. Yeah, if there is no SED variation, so if there is no SED, yes, if there is no SED variation between clouds, then we would see a depolarization without EVPA rotation. So we would see a decrease. So we would see that, but with a similar spread in the two distribution of EVPA differences here. So to search for line of sight frequency decorrelation, we decided to take the spread of the EVPA difference distribution as indicating whether or not there is this effect is in the data. So yeah, and we call it, so that we quantify the spread with D being the circular standard deviation of the difference between the polarization angle at the two frequencies. And we measure D in the control sample and the target sample. And as we can see here on the plot, we have a significant excess of target as compared to control. The band here represent the sampling uncertainties of the sample. And this huge excess is robust against CMB estimate and residual systematics. Okay. But there is something that I didn't yet mention, is that because there is a depolarization in the line of sight, we can expect a larger level of noise in the target sample as compared to control sample. So, and what is the effect of noise in the dispersion measure? Well, it increased D, right? So it is part of the noise can mimic somehow the effect of a line of sight frequency decorrelation in D. So one has to account for this noise difference when looking at those two distributions, say. And to do that, we we developed a method that allow us to produce a simulated target sample where we know there is no lines of sight frequency decorrelation. So we decided to have to use a bootstrap resampling, a weighted bootstrap resampling, so that in our resample sample we have a data set that is at the same size of the data set that we are considering, and we have a same level of noise. And to do that, we resample the control sample where we know by constriction that there is no line of sight frequency decorrelation. Here we show that the per pixel interfrequency uncertainties in control is indeed larger in target than in control, as it is expected if we have polarization. And we show here that the weighting, the weighted resampling actually works at reproducing simulated data set with a noise as large as in the observed target sample. Okay, and now for each draw, we recompute this quantity D, and we just obtain a distribution of D value, of D value, and any remaining excess in D would be due not to the noise, because the reason we shift the distribution is because of the noise, but if we observe something even larger, that is because of line of sight frequency decorrelation, and thus of SED variation in dust clouds. Okay, so in a way, computing computing the p-value, so the p-value of the observation in orange here as compared to the blue histogram, give us the probability that the target sample, the observed target sample, be due only to the noise in Planck data. And the result of our analysis is that the probability that the observed target is just due to the noise is as low as 5%, or down to 4 10 to the minus 7, depending on the exact combination of CMB subtraction and the exact set of polarization map that we use, polarization map that are being obtained with different algorithm of map making. And we summarize in this part here all the subtraction of different CMB estimate from different component separation algorithm, Commander, Niels, Evans, Mika, or no removing of the CMB, and we show the distribution of target, but without line of sight frequency decorrelation, and the measurement of the target sample, and we see that the difference is always significant, at least at 2 sigma level. So we prove this signature to be robust against CMB estimate, as I just said, robust against residual systematic in Planck, and that we do it by repeating the analysis on different set of polarization map. And we checked that this claim is also robust against specific choice in the pixel selection, and also in different cut that we had to impose during the analysis. So we are kind of confident that this is the first observational evidence of line of sight frequency decorrelation. And we observed it in the noisy Planck data. We were so happy with this with this result that we wanted to go further. And we look at the data in more details, and we were kind of happy seeing that all the phenomenological expectation from a simple model are met with the Planck data. Here, maybe you remember that I told you that the more the angle between the plane of sky orientation of the magnetic field will be large, the more we will have an EVPA rotation between the two frequencies, which means that the more the D value will be large, the more this offset angle between magnetic field is large. And we looked for it in the data. So we take all the pixels that show a complex, that show at least, well, that show some complexity in terms of H1 velocities. And we bin the data according to the angle that the magnetic field make in the different velocity range. And then we look at the polarization map for each bin of pixels. And we see this very nice correlation here, which is as expected. The more the magnetic field is misaligned, the more we will see line of sight frequency decorrelation effects. Okay, and we also observed a decrease in the degree of polarization at the two frequency, but this is not shown here. And we even move one step further by asking the question of how much SED variation do we need from cloud to cloud to explain the amplitude of the signal that we are observing. To do that, we derived a first phenomenological model which relies on the H1 data, orientation data to, well, H1 data, to model the per cloud dust, the Stokes parameters for each cloud at a given frequency. And then we assume that that the ratio of the Stokes parameters per clouds between the two frequencies is follows this relation here, which means that the intrinsic SED variation is not zero, but it is a normal distribution about zero with that parameter, the spread here, sigma rho, quantifying this intrinsic SED variation from cloud to cloud. And so we use H1 data to model the Stokes parameters at a given frequency. We use this modeling to predict what is the Stokes parameter at the other frequency. And then we can compute by summing the density, summing the signal for each cloud. We can model the emission at a given frequency, compute the polarization angle, and compare the polarization angle at the two frequencies. Okay, and then for a sample we have EVPA differences with different frequencies, and we can measure our statistic D here for different value of the intrinsic SED variation. And we found that the dust SED must vary at the level of 15% to explain the observation between the polarized intensities at 217 and 353. So this brings me to my summary. So we used in that paper, we used the latest knowledge of the magnetized dust ISM that can be drawn from H1 based data sets. And we used that huge amount of data only to divide the sky in different samples that should not show any line of sight frequency decorrelation, and a sample that maximized the likelihood of showing the effect of line of sight frequency decorrelation. And that sky pixel selection is fully agnostic to polarization data. Then we move to the Planck polarization data at high frequencies, 217 and 353 gigahertz. We remove all the CMB measurements that estimate that are available, and we measure EVPA difference between the two frequencies. And we did that for the two samples, the one that has no reason to show any line of sight frequency decorrelation, and one that we suspect could show line of sight frequency decorrelation. And remarkably, we met all phenomenological expectation. We see the polarization, and we see a larger dispersion of EVPA difference in the sample. And the excess that is observed in EVPA difference persists, and it cannot be the result of an artifact of CMB subtraction or of residual systematic in the Planck polarization map. And it cannot be it cannot be explained by noise in the data. So we draw the signature, well, we consider those as a signature of line of sight frequency decorrelation, that we observed. So the takeaway message is that there is a line of sight frequency decorrelation. It does exist, and we were able to measure it in Planck high frequency data. And we were able to do so because we knew where to look for the effects. These lines of sight involves, well, they are, as I showed, they are scattered on the sky, and this might be an important point. And we were able to quantify the SED variation that is necessary to explain the effect that we are observing. I kind of promised that I was about to discuss what are the implications of this effect for CMB mode searches, but it's too early to do such a claim because further work are necessary. In this analysis, we have learned a few things. First, as I just said, the effect exists, and it stands above the noise in Planck data. So as soon as the noise level will decrease with ongoing and future experiments, we will have to wonder about, well, we will have to account seriously for this for this effect. We also, what I wanted to point out as well is that what we see here is that at the pixel level, so at the map level, we have a decorrelation where we have a rotation of EVPA of the dust emission. And so a frequency extrapolation of foregrounds model could be risky at the map level, depending on the region, on the sky region we focus on. And this is an important input, I think, for a CMB experiment, which does that routinely, as I said earlier. And what we also showed in that paper is that, well, confirmed with that study, is that the knowledge of the magnetized ISM is and will be valuable in the topic of CMB mode searches. And for any of you that want more details on this on this study, the paper will hopefully soon be posted on archive. Thank you.
Thank you very much, Vincent. Any questions? You can either raise your hand or just turn on your microphone and ask. Ebba?
Hi, Vincent. It's really nice to see you and see these really nice results. So I wanted to ask you, what is the precision by which you know the angle between the clouds? I doubt this would affect the results very much, but just out of curiosity.
Yeah, you mean from the H1 data? There is so in the H1 orientation data, there is no uncertainties that are given. It is known that the H1 orientation doesn't trace exactly the magnetic field. There is an astrophysical scatter between the H1 fibers orientation and the magnetic field. So I suspect this scatter to be the dominant factor here, But as we see here on this plot, there is a clear effect, a clear correlation between the decorrelation and the angle. If you have some noise with the H1 orientation data, then well, it won't kill the correlation that we see here.
This is what I suspected. Thanks.
Other questions?
Can I ask a question?
Yeah, fine.
Hello, Vince. Thank you very much for the presentation. You have done a lot of work in this topic. And I would like to ask something regarding your slide 29, because there were many plots and I couldn't understand everything here.
This one?
Yes.
So,
I was wondering about the bottom panel. In the bottom panel, so you're showing control and target, the distributions, but in the target, where you have this complexity along the line of sight, why shouldn't the peak of the distribution should be a little bit offset from zero?
So, well, the thing is, so for one line of sight, as in the case of the tomography region here.
Yes.
Yeah.
Okay.
So indeed, we have an offset. Okay.
Mm-hmm.
But if you consider a large ensemble of lines of sight, there is no guarantee that the two clouds will have a different SEDs, right? So it might be zero as well, even though the angle between the magnetic field is different. But also you can have, here you have 8 degrees, but it could be -8 degrees.
Oh, yeah.
And
yeah.
it can be anything in between.
Yeah,
right?
you're right.
So now with the correct, how to say, anyway, things will add up and you will end up with a Gaussian distribution. That is the expectation and the underlying assumption there. Yeah.
Okay, so that's why you attribute everything to the scatter of this distribution.
Yes, that's the reason we consider scatter as being, well.
Yeah, you are right. Okay. Okay, thanks. Nice. Well done.
Anything else for Vincent?
I also have a question about this particular slide. So Vince, first of all, very, very interesting talk. Thank you. So you mentioned that when you have multiple clouds, say 2, if the magnetic field is 90 degrees, is different by 90 degrees in direction, then you would expect zero polarization.
Yes.
Does the background radiation play any role on this, if it is polarized or not? So if you have polarized radiation behind the clouds, or zero polarized, does it play any role?
Yeah, well, it does. And so you have, so if you take the map, the observed sky at 353 gigahertz and at 217 gigahertz, and then you do nothing on the map first and just compare the angles between the two, then there will be a change in the EVPA that is attributed to the CMB indeed, because the CMB and the dust, they have different SEDs. Right. This is how component separation method get out the CMB. Right. But what we did, so now if we consider an ensemble of lines of sight, then it is true that the CMB will produce an increased scatter in the distribution. But we accounted for that in removing CMB estimates in the frequency polarization maps.
All right, thanks.
Is there another one from Rafael?
So no, it's sorry, it's okay.
All right. Anything else for Vincent?
Can I ask one?
Yeah, Nico.
Maybe excellent talk, Vincent, and superb work. Maybe you said it and I didn't get it. You select a bunch of points as the control and many more points for the where you suspect or you know from the work of Gina that there are at least two clouds overlapping. If you selected a large number, but the best cases, would you make the disagreement harder and more obvious, that is more sigma?
So
If you had less points, you have many points. So extracting someone's which may have 3 or 4 clouds or something else and so on, wouldn't it strengthen the result?
so
At least to the eye, yes.
Yeah, so I think there is two competing effect here. One is the size of the sample. The more data point we have, the stronger the excess will be. The larger the excess will be, because well we are looking into noisy data. So the more data you have, the best you have. Now, it is true, and we have carried some tests in that direction, that if we impose some quality criteria, both at the sample selection, but also at the polarization, in the polarization data, we could improve the detection, but we didn't try to optimize the significance of the effect. We didn't try it. Yeah. Now there is another answer to your question, I think, which is based on the H1 data. We don't really have any access to the SEDs of the dust cloud. Okay, so we can select 10 lines of sight with a very good geometrical configuration, but we have no idea about the SEDs. They could be 2 clouds, very misaligned, with the same column density, so that would be perfect to detect the lines of sight frequency decorrelation if they have a difference in temperature or dust emissivity, right? But if they don't, then we would get 0. Doesn't mean that the effect is not up there. Does it answer your question?
Yes, thank you.
Okay, any other quick question for Vincent? All right, if not, let's all thank him very much again, and thank you all for joining us, and we will see you next time. Bye, everybody.